Right, here we have another question now, and we've got someone sitting on a little cart, and this is what I've done in class, having a student sitting on like a little board, and another student applies a force to them, and then of course they accelerate forwards. So we're going to ignore friction again here. So we have our floor there, and we're going to ignore the friction that's between the wheel and the floor going backwards. There will be some. Of course, you know that if you ever pushed anyone on a skateboard, that they will accelerate in one direction, but then of course they slow down. Why? They slow down because of friction pushing them back the other way, and of course there's a bit of air friction as well. If you were to put them on some ice, like on an ice rink, and push them, because there's less friction between the wheels and the ice, they go further. Anyway, we're ignoring it. So let's have a look at the problem. We've got this scenario here. We can simplify it just by drawing a box. We're ignoring friction. What have we got? We've got a force that's being applied that way, 64.2 newtons. So let's write that in. We're ignoring a backwards force due to friction. We've got to know that the mass is equal to 51 kilograms. We've got to calculate the acceleration again. So pretty much the same as the last question. We've got F equals ma, and it's the sum of all the forces in the x direction. Well, because we're ignoring friction, there's only one force now, and that's going towards the right, right? So we've got a mass of 51 kilograms, and we want to work out A. Well, we don't know A, so I guess I can just put A there. We know the force here is 64.2. So yet again, we go, okay, acceleration is equal to 64.2 divided by 51. What do we get? All right, 64.2 divided by 51. We get an acceleration of 1.26 meters per second squared. And that, of course, is to the right. Now, how would that change if we did actually include some friction now? So let's just say that we have a frictional force going backwards, right? And that pen's getting too thick, right? So we've got a frictional force going back. Let's say that is going to be, let's give that 1.7 newtons. Okay, so how does that change things? Well, let's redraw our diagram now. So we've got our box. We've got a applied force going at 64.2 newtons. We now have another force coming back, which is the frictional force. Right, so we've got a force due to friction. That's 1.7 newtons. Okay, yeah, that makes sense. Now, of course, this is along the x-axis, and remember we said that the x-axis, anything towards the right is going to be positive, and anything towards the left is going to be counted as negative. So let's sum the forces now. So we've got the sum of the forces is we have 64.2, right, plus all the force going in the opposite direction now, which is that, so it's minus 1.7. So what does that give us? 64.2 minus 1.7, 62.5. Okay, and that's 62.5 towards the right. All right, so now let's see what the acceleration would be. So we write our equation, sum of the forces is equal to mass times acceleration. Well, we just found the sum of the forces. Okay, so that's that number, 62.5. The mass is the same as before, 51 kilograms, and we need to calculate A. So A is equal to 62.5 divided by 51. Let's see what we get here. 62.5 divided by 51. 1.2, and I'll just round that to 3 meters per second squared. So you can see that it's a smaller value than what we had before, which makes sense because here there was no friction, there was no force opposing motion, right? Slowing you down, making it harder to push. So therefore you had a greater acceleration. However, in the second example where we have a bit of friction acting in the opposite direction to the applied force, so it makes it harder to push, and even when you get that acceleration going, it's slowing you down because of friction, and so the acceleration is slower. Makes sense, hopefully. Okay, so that's some calculations using F equals ma. First of all, in a simple situation where there's no opposing force, no friction, we're ignoring it. Then another slightly more advanced problem where we have friction, but really all we're doing is we're summing the forces. Newton's second law is the sum of the forces is equal to the mass times acceleration. Okay, and here we can see in the x direction we sum the forces together, find out the net result. So sometimes you might see it in books as net, right? And then that's how you do it. Hopefully that makes sense to you. And the exact same principles happen if you're going up or down, right? If you're trying to work out forces going up or down, same thing. All right, hopefully that makes sense. See you in the next video.